Hi, let's now return to the simple harmonic oscillator problem. We have already discussed the simple harmonic oscillator problem in the Dirac picture. Right? We talked about in the Dirac method actually. We called it the Dirac method, where we defined the creation and annihilation operators, and in the end we found the energy eigenvalue spectrum. But we said nothing about the time development of the system. Right? How does the system evolve in time? Right? About this thing, we did not say anything. Now, if you want to look at the time evolution of the system, as we know, there are two ways to look at it. You can either talk about it in the Schrodinger picture, or you can discuss the time evolution in the Heisenberg picture. In the Schrodinger picture, as we know, the operators don't change with time, and states evolve in time according to Schrodinger equation. Okay. In the Heisenberg picture, the states do not change, and the operators evolve according to Heisenberg's equation of motion. All right. So we'll look at the simple harmonic oscillator problem in the Schrodinger picture as well as in the Heisenberg picture. Now in the Schrodinger picture, we'll be specifically working on the coordinate representation or the position representation. We'll be discussing the problem in the coordinate representation, which means that we'll be writing the Schrodinger's wave equation and we'll try to solve it. And by solving it, we'll get the energy eigenvalues as well as the energy eigenfunctions, and then we'll see how it evolves in time. All right. Now, before going into these things, we'll have a quick review of some of the concepts that we have discussed before. Okay. First, we'll make a quick revision of the time-dependent and time-independent Schrodinger equations. Even though we have discussed these things in the class, I would like to revise it in a slightly different manner from what we have already seen. Okay. And then I shall revise the Hermite polynomial. Okay. Now, the mathematics that we need to solve the Schrodinger equation for simple harmonic oscillator potential is that of Hermite polynomials. Okay. Now, you have already studied these things. You have already solved the differential equations, the Hermite differential equation in your mathematical physics course. Okay. So we shall not be solving the equation here. We'll just look at the equation. We'll just look at the differential equation. We'll look at the solutions and some of the properties necessary for us. Okay. Now, if you don't want the revision part, you can fast forward directly to the Schrodinger picture. All right. Now, if you think it might be useful to look at to revise some of this concept, you can start in the beginning. All right. So I leave that up to you. Now, here is the Schrodinger wave equation. The Schrodinger wave equation also has this form. It's IH bar partial derivative of the wave function with respect to time is equal to H psi of x comma t. All right, let's work in one dimension, so we don't write vectors. Okay. Now we just write the Hamiltonian as Hamiltonian is equal to p square divided by 2m operator plus v of x. Okay. So this is the Hamiltonian operator. Right? Now, if you're working in the coordinate basis or in the position representation, we write p, the momentum operator, is minus ih bar partial derivative with respect to x, right? And the potential operator, right, v of x is equal to, this is simply v of x, a function of x, right? It's a function of position. All right. Now we can find p square from it, and then you substitute it back in here, right, or back in here. Okay, just write the Hamiltonian in the position representation using these things, and then we'll end up with this equation. We have already done this. Okay, I'm just revising it so we don't go into the detailed mathematical steps. Okay. Now we shall consider a particle in one dimension moving in a time-independent potential v of x. Right? So in the case of time-independent potential, we can actually see that the Schrodinger equation can be separated into two different equations. Right? Now this can be seen by taking psi of x comma t as u of x multiplied by f of t. All right? So we are trying a solution of this form where the spatial dependence and the time dependence are separate. All right. Now, if we substitute this into a Schrodinger equation, right, this solution, this form of the solution to a Schrodinger equation, we'll see that the equations nicely separate into two different equations, right? One differential equation with respect to time and another differential equation involving derivatives with respect to space. Okay. Now we'll see that this can happen only if v of x does not depend on time. Now let's substitute this assumed form psi of x comma t is equal to u of x multiplied by f of t. All right, let's substitute this assumed form into the Schrodinger equation. And of course, the Schrodinger equation is IH bar partial derivative of psi of x comma t with respect to time. This is equal to minus h bar square divided by 2m. Take the partial derivative with respect to x twice of the wave function plus v of x psi of x comma t. All right. Now we substitute this form of the solution. Okay. And we notice that on the left hand side we have a derivative with respect to time only. So this derivative with respect to time does not affect our u of x. Right? So on the left hand side, u of x can be treated as a constant. So if we substitute psi is equal to u multiplied by f in here, this becomes ih bar u of x and then df by dt. Okay. So notice here that I have replaced the partial derivative with the normal derivative. Okay, the reason why I do this is because f depends only on time, f depends only on t. Okay, so it doesn't matter whether it's a partial derivative or a normal derivative, it's the same thing. All right. So on the right hand side, we have got minus h bar square divided by 2m. This is a derivative. All right, this is the second derivative with respect to x. And again, it does not affect our f of t part. So this f of t part can be taken, can be separated out. We get only a second derivative. Right, again, I can write this as the normal derivative d square by dx square of u of x. Right, and this term becomes v of x u of x f of t. Okay, this part, right? This is v of x multiplied by u of x f of t. Now we see that there's a u of x here and a derivative with respect to time. Here we have got derivative of u of x, right, and a function of time. Right? We see that the function of space can be removed from the left hand side and the function of time can be removed from the right hand side if we divide throughout by u of x multiplied by f of t. So we divide throughout by u of x multiplied by f of t. Okay. So when we divide throughout by u of x multiplied by f of t, the u of x here gets cancelled and I have got ih bar divided by f of t. Okay. df by dt is equal to minus h bar square divided by 2m. All right. Here the f of t gets cancelled with this f of t and we have got a u of x in the denominator. Okay, I'll write this as 2mu of x and then d square u of x by dx square plus v of x, because this u of x multiplied by f of t simply gets cancelled. All right, so that's the form of the equation that I have here. 1 by f ih bar df by dt is equal to minus h bar square divided by 2mu d square u by dx square plus v of x. All right, notice that instead of the partial derivative, I have simply written the normal derivative. All right. This is the equation. So if we look at it, we see that the right hand side is independent of t. There is no time dependent term in here. Right? And the left hand side is independent of x. Right? Now this means that both sides must be independent of x and t. Left hand side is independent of x, right hand side is independent of t. Okay, this means that both these sides have to be independent of x and t. Only then we can have an equality of this form. Right? This means that the left hand side and right hand side must be equal to a constant. Let's call this as E. Right? So we can write two equations now. We have separated the equations. IH bar, let me write as 1 by f df by dt equal to E. That's one equation. Or we can write the f on the other side. So we can write this as IH bar df by dt is equal to EF. Okay. And the right hand side can be separately equated with E, and this becomes minus h bar square divided by 2m d square u by dx square plus v of x. Okay, there's a u in the denominator here, right? This is equal to, as we said, E. All right. Now we can multiply throughout by u, so the u will disappear from the denominator here. There will be a u right here. Right? So we get two equations. We get two differential equations. IH bar df by dt is equal to EF and minus h bar square divided by 2m d square u by dx square plus v of x multiplied by u is equal to E. Right? We have separated the Schrodinger equation into two different equations. All right. Now note that this would have been possible only if V, or the potential, was independent of time. Right? If the potential depended on time, we couldn't have separated it in this manner. Okay. So this is the first equation. IH bar df by dt is equal to E multiplied by f of t. Okay. Now this equation can be solved. Immediately we see that we can write this as df by dt is equal to E divided by IH bar f of t. So we take a derivative with respect to time, we get something multiplied by the same function, right? Or I can write this as minus IE by h bar f of t. Right? So we take the derivative, we get something multiplied by the same function. Now we see that this is clearly the exponential function. So we can write this as exponential minus IET by h bar. Because if you take the derivative of this function once, you will get minus IE divided by h bar multiplied by f of t. Okay, so clearly this function satisfies this equation. So we can say that f of t is proportional to exponential minus IET by h bar. This is solved easily, right? And the second equation is minus h bar square divided by 2m d square u of x by dx square plus v of x u of x is equal to E multiplied by u of x. Now this is in the form of eigenvalue equation, right? And this part is called the time independent Schrodinger equation, right? This is called the time independent Schrodinger equation. And clearly this is an eigenvalue equation for the function u of x. We have got the Hamiltonian operator acting on u of x to give a constant E multiplied by u of x. Okay, this is an eigenvalue equation. So this u of x here are the energy eigenfunctions. These are the energy eigenfunctions. All right. So the Hamiltonian acting on the wave function gives a constant multiplied by the same wave function. This means that the time independent wave equation, is the energy eigenvalue equation in coordinate representation. What we have just written down is the energy eigenvalue equation in the coordinate representation. Okay, so there may be other eigenvalues and eigenfunctions that satisfies the above equation. Right, so we know that there could be a number of eigenvalues corresponding to a given operator. Right? So we can write in general, we can write this in general as minus h bar square divided by 2m d square un by dx square. Right? So we are just labeling the eigenvalues by the index n, and the corresponding eigenfunctions are given as un of x. Right? So minus h bar square divided by 2m d square un of x by dx square plus v of x, okay, plus v of x multiplied by un of x. Okay, actually there was a mistake here. This un of x should not be here because there's a bracket. All right, I'll correct it in the notes. So this is minus h bar square divided by 2m d square by dx square plus v of x acting on un of x equal to en multiplied by un of x. Okay, now this n, as we said, labels the eigenvalue. Right, so un of x is the eigenfunction of the Hamiltonian corresponding to the eigenvalue En. The eigenvalues and eigenfunctions are labeled by this index n. Okay. Now the solution that we are looking for corresponds to each value of n. So we can write psi of x comma t is equal to un multiplied by f of t. This was the form of the solution that we were looking at. Okay, and this is written as un multiplied by e raised to minus ient by h bar, because we already found that f of t is equal to e raised to minus ient by h bar. All right, now the psi of x comma t here, it is called a stationary state, which we have already seen. Okay, the reason that we can see from here is that if we take the modulus square of this, we see that there is no time dependence. Okay, the probability density is independent of t. And we have seen that various expectation values also will remain independent of t if the state is a stationary state. All right. So the psi n above describes a stationary state in which none of the particle characteristics change with time. Right? We have discussed these things already in a slightly different context, but I hope you can make the connection here. Okay, we had actually proved that the expectation values of any operator will remain the same in a stationary state. right, if the system is in a stationary state. Now we have to notice that the Schrodinger equation is obeyed by any psi n of x comma t. Right? If there are a number of energy eigenfunctions, let's say psi 1 of x comma t, psi 2 of x comma t, etc., all of them are solutions to the Schrodinger equation, right? Which means that if we take a linear combination of all this, they also, that the linear combination also will be a solution to the Schrodinger equation, which means that the general solution can be written as a linear combination of all these energy eigenfunctions or all the stationary states, right? So the general solution would be psi of x comma t is equal to sum over n. There would be some expansion coefficients which we can call as Cn, and then psi n of x comma t. This would be the general form of a solution, right? Which means that the system need not be in an energy eigenstate. It could be in a superposition of energy eigenstates. Now it's time to quickly revise our orthonormal Hermite functions. All right. Now you have studied these things in your mathematical physics course. All right. And you have done the hard work over there. You know the equations, right, to which Hermite functions are the solutions. You have solved them using the Frobenius method or the series solution method. Right? You have studied the properties of the solutions. Okay? Which means that we won't be doing all that thing again. You have already done the hard work. We'll just take the results from there. Right? You already know how to do these things. So we shall not repeat the same steps. We'll just take the solutions from there. Right? So let's take a quick look at the Hermite functions. Right? Now, Hermite polynomials are solutions to a differential equation. Right? So if you have a differential equation of this form, the solution to this equation, to this differential equation, are known as Hermite polynomials. Okay, and these are denoted by hn of x. So if you have y double prime minus 2xy double prime plus 2ny equal to 0, where y prime is dy by dx and y double prime is d square y by dx square, right? And if we write out this the solution to this equation, the solutions are denoted as hn of x, and these are called as the Hermite polynomials. Now, using the Hermite polynomials, we can also define a Hermite orthonormal functions, the Hermite orthonormal functions. So you have seen that we can define phi n of x, the Hermite orthonormal functions, as we have got this normalization factor and then e raised to minus x square by 2 hn of x. Alright, so hn of x themselves do not form orthonormal functions, but we can construct orthonormal functions out of them. Right? These orthonormal functions will call us phi n of x. Phi n of x equal to 1 divided by square root of pi 2 raised to n factorial whole raised to 1 by 2 and e raised to minus x square by 2 multiplied by hn of x. Okay. Now phi n themselves, the orthonormal Hermite functions themselves, satisfies the differential equation of this form, phi n double prime plus 1 plus 2n minus x square phi n is equal to 0. Which means that if we have a differential equation of this form, right, the solution to this equation would be the orthonormal Hermite functions, which are given by phi n of x. Okay, here again, phi n double prime means taking the derivative of phi n twice with respect to x. Okay, this would be d square phi n by dx square. And these are called orthonormal Hermite functions because they satisfy the following orthonormality relationship. Okay, we can write this as integral minus infinity to infinity phi n star phi m is equal to phi n star phi m dx is equal to delta nm. Okay, you might have seen that this is equal to 1 only if n is equal to m. And if n is not equal to m, then this integral is 0. All right. Now this is denoted as phi n comma phi m in a bracket. Right. So if we have two functions, this is a notation that we might be using again. If we have two functions psi comma phi in a bracket, right? This bracket here, right, this is called the inner product of two functions. It is defined as minus infinity to infinity psi star phi. All right, you take the first thing in the bracket or the prefactor, and you have to take the complex conjugate, and then simply write the post factor phi itself, and then you have to integrate this over all space. Right, this is the definition for this bracket of two functions. All right, psi comma phi. Now you may remember that this is exactly how we represent an inner product in the position space. Okay. Now we have all the tools to start discussing the simple harmonic oscillator problem in the coordinate basis. Okay, we have already seen the algebraic or Dirac method. Over there, we obtained the simple harmonic oscillator eigenvalues and even the eigenkets without ever solving any differential equations. Okay, we worked purely algebraically. We also had not looked at any time development of the system. Right, we just found the eigenvalues and eigenkets. We did not discuss how these things evolve with time. Right, so the time evolution, as we know, can be studied either in the Heisenberg or the Schrodinger picture. Also, in the algebraic method, the calculations were independent of the representation. Right? We did not choose any specific representation. We just did abstract algebra. We defined these creation annihilation operators, got their commutators from the canonical commutation relations, and then proceeded completely algebraically without going into any specific representation. All right. But in what follows, we shall be working specifically in the coordinate representation, which means that we'll be taking the eigenfunctions or the eigenkets of the position operator as the basis. All right. So now what we are going to do is that we'll do both Schrodinger and Heisenberg pictures, but we'll be working in the coordinate representation, right? Unlike in the Dirac method. Let's now discuss the simple harmonic oscillator problem in the Schrodinger picture. As we said before, we shall be working in the coordinate representation. Okay? We start with the simple harmonic oscillator Hamiltonian, which we are already familiar with. Right? We already used this Hamiltonian when we solved it in the Dirac method. Okay? So the Hamiltonian is h is equal to p square by 2m plus half kx square. All right. Now again, in the coordinate representation, we know that the momentum operator is written as minus I h bar d by dx, right? And the position operator is simply x. The Hamiltonian in the coordinate representation then becomes, right? So if I take p square divided by 2m, this becomes minus h bar square divided by 2m d square by dx square plus half kx square. So this is the simple harmonic oscillator Hamiltonian in the coordinate representation. This is the form of the Hamiltonian that we need to use when we work in the coordinate representation. Okay. Let's look into a time-independent Schrodinger equation for the simple harmonic oscillator. Okay. The time-independent Schrodinger equation has this form: h un of x is equal to en un of x. Now instead of h, we write it in the coordinate representation like this. It's minus h bar square divided by 2m d square by dx square. This is the kinetic energy part. This is the potential energy part, half kx square. Right? Acting on un of x gives you a constant multiplied by un of x. This is the energy eigenvalue equation in the coordinate representation. All right. Now we can slightly rearrange the terms in here. So what we do is we multiply throughout by this minus, okay, and it becomes h bar square divided by 2m d square by dx square. Let me write as d square un of x by dx square minus half. This k is m omega square as usual, so we can write this as m omega square x square. All right. This is equal to en minus en un of x, because we have multiplied throughout with the minus sign, with the minus 1. Now we can take this en to the left side, and this becomes h bar square divided by 2m d square un of x by dx square, okay, plus en minus half m omega square x square acting on un of x, or multiplied by un of x. This is equal to 0. Okay, so here we have simply used k is equal to m omega square. Right? Now this is the time independent Schrodinger equation that we need to solve. So this is a differential equation, okay, of un of x. We have to solve this to get un of x. Right? Well, not just the eigenfunctions, also the eigenvalues. So we can find both the eigenfunctions and eigenvalues by solving this equation. Right? This is the equation that we ended up with. Right? Now if you look at this, this actually looks rather similar, somewhat similar to the equation obeyed by the orthonormal Hermite polynomials. Now this was the equation obeyed by the orthonormal Hermite polynomials. It's written as d square phi n by d zeta square plus 1 plus 2n minus zeta square phi n of zeta is equal to 0. Okay? It's somewhat similar, but not exactly the same. All right. So what we'll have to do is that we'll have to massage this equation a little bit, right? We'll change things around a little bit to bring it exactly into this form. Now, once we do that, our work is done, right? Because once we do this, then we know that the solutions are the orthonormal Hermite polynomials. Okay. Now, we have already solved this equation before, right? And we don't have to do that again, right? We can just look up the mathematical physics textbook, all right? You can just look up your Afghan, right? The textbook by Afghan, and the solutions are already there. So the only work we need to do now is to bring this equation to this form. Okay. Now the first thing we can do is that we see that in here there's an En. All right. So it has the dimensions of energy. Okay. So over here we have got some 1 plus 2n minus zeta square. This n was a number, if I remember it right. Okay. So these don't have any dimensions, all right? So let's first make every term dimensionless, all right? Let's make it all dimensionless. Now, what's the best way to make it dimensionless? You just divide throughout by h bar omega, which is 1 unit of energy, all right? So we take this equation, the time-independent Schrodinger equation for the simple harmonic oscillator, and divide throughout by h bar omega. Okay, so let me write it here. It becomes here it becomes, there's an h bar square here. So when you divide by h bar omega, one of the h bar cancels, and we have got h bar divided by 2m omega. Okay, and d square un of x by dx square plus this becomes en divided by h bar omega minus half m. Now if you divide this thing by h bar omega, one of the omega gets cancelled. So this is half m omega divided by h bar, and we have got x square, un of x equal to 0. All right. Now still it's not in this form. It's not completely in this form. All right. So we see that the main difference here is that over here we have got a derivative with respect to zeta square. All right. And in here it should be a minus zeta square. It has to be a minus zeta square. Okay. So whatever the variable over here is, we should have the square of the same variable over here. That's not exactly what's happening here. All right. First of all, we don't have d square by dx square just in this form. We have a factor h bar divided by 2m omega. Right. And we don't have minus x square here. Instead of minus x square, we have got half m omega by h bar x square. All right. Now, I think this can be fixed because here we have got x square. Here we have got a derivative with respect to x square. So we just make a change of variables, right? Now, before that, we see that we could do this, all right? Because the x square here in a way appears in the denominator, right? Appears in the denominator in a way, all right? This dx square appears in the denominator. This x square appears in the numerator, okay? And we see that we have got an h bar by 2m omega here, and we have got half m omega by h bar here. Right? Now, if we look at this, if we don't have this 2 here, right? We have got h bar m omega here, and here we have got m omega by h bar. They would be perfectly reciprocals of each other, right? Then we could make some substitution because we could think of this x square as something that appears in the denominator, right? We are just what do you say, inspecting this equation, right? We are not saying anything rigorous here. We are just inspecting, right? So in effect, this x square is in the denominator. We have got this x square in the numerator, right? Here actually we have got m omega by h bar x square. Here we would have something like m omega by h bar x square in the denominator if this 2 wasn't here, right? So that 2 is kind of problematic there. So let's multiply throughout by 2. Okay, so this 2 would cancel and we will get h bar m omega, so h bar divided by m omega d square un by dx square plus, okay, here you would have 2 en by h bar omega minus m omega by h bar x square un of x equal to 0. All right. Now we see that we are getting very near to this form. We are getting very near to this form. All right. Because we can write this h bar divided by m omega as 1 by m omega by h bar. All right. So I can write this as 1 divided by m omega by h bar. All right. Now we see that if my variable of differentiation was m omega by h bar, actually square root of m omega by h bar multiplied by x instead of x, right? So instead of x, if I had, all right, let's say instead of x square, you can look here, instead of x square, if I had square root of m omega divided by h bar, sorry, we are looking at it from here. So instead of x square here, if we had m omega by h bar x square. So if we take x square going to m omega by h bar x square, then it seems that the work will be done. It seems that the work will be done, right? Because here we have got dx square, right? And we also have this m omega by h bar in the denominator, right? So why not make the substitution? X square is equal to m omega by h bar, sorry, why don't we substitute x square by m omega by h bar x square? Or rather, we'll change the variable x into square root of m omega by h bar x. Right? We just take the square root here. So we see that this form of the equation suggests a substitution of this form, right? Instead of x, if we put square root of m omega by h bar x, then it seems that we'll get this form of the equation, right? This is all just inspection, right? We are just looking at the equation. Okay? This means that we should try a substitution like this. So instead of x, we'll write variable zeta. Zeta is equal to square root of m omega by h bar multiplied by x. Let's try this substitution. Let's try this substitution. Okay. Now, before doing that, let's just go through the argument once again. Note that the coefficient of phi is the dimensionless quantity 1 plus 2n minus zeta square. Now, in the simple harmonic oscillator equation, the coefficient of un has dimensions of energy. Right? So, to make a comparison, we first make the coefficient of un dimensionless by dividing throughout by h bar omega, which has units of energy. Right? And that gives us this equation, which we already wrote down. Now we note that the coefficients of d square un by dx square and x square are reciprocals of each other, except for the 2 in the denominator of both terms. Right? See, this coefficient of d square un by dx square here, which is h bar by 2m omega, and the coefficient of x square, it is half m omega by h bar. So they are actually reciprocals of each other, except for this factor of 2. So let's get rid of the factor 2 by multiplying by 2 throughout. So we multiply throughout by 2 to get h bar by m omega d square un by dx square plus 2en by h bar omega minus m omega by h bar x square un of x equal to 0. Now this equation, right, we have brought the time independent Schrodinger equation to this form. Right? This equation suggests changing the variable from x to square root of m omega by h bar multiplied by x. This should solve our problem. So we write zeta is equal to, we define a new variable, zeta is equal to square root of m omega by h bar multiplied by x, which can also be written as alpha x, where alpha obviously is square root of m omega divided by h bar. There's no x here. Alpha is square root of m omega divided by h bar. Okay. So let's try the substitution. Zeta is equal to square root of m omega by h bar multiplied by x. Okay. First, we need to see how the derivative changes. Okay. We know that the derivatives change according to this rule. If we have d by dx, we can write this as d zeta by dx multiplied by d by d zeta. Okay. This is exactly what we will do here. So here we have got d square u by dx square, which can be written as d by dx of du by dx. Okay, and d by dx by this rule can be written as d zeta by dx multiplied by d by d zeta. Okay, and then the bracket. Inside the bracket also we have a d by dx, which is written as again d zeta by dx multiplied by d by d zeta. Okay, so we change this d by dx and this d by dx according to this rule. That's all. Okay. Now this d zeta by dx, we see from here that d zeta by dx is equal to square root of m omega by h bar. This is square root of m omega by h bar. D zeta by dx is square root of m omega by h bar. All right. So let's write this like this. This d zeta by dx is square root of m omega by h bar. And we have a d by d zeta here. Okay. And inside the bracket, again, we have got a d zeta by dx, which is again square root of m omega by h bar, and then du by d zeta. Okay, actually there was a small mistake in this step. I shall correct that in the notes. Okay, and this becomes, so this is a constant and it gets multiplied, so this simply becomes m omega by h bar d square u by d zeta square. So instead of d square u by dx square, we can write m omega by h bar d square u by d zeta square. All right, that's how that term changes. Okay, now we are making the substitution. We are changing the variable from x to zeta. Okay, so what we have is a function of x, which we write as un of x. Now we change the variable, it becomes un of, we can write this as zeta by alpha. That's fine. All right, now this un of zeta by alpha will be some function of zeta. All right, it won't be the same function un, it will be some other function. We'll call it as phi n. All right, so this un of zeta by alpha will call some function phi n of zeta. Obviously this is a function of zeta, right? But it's not the same function un. It's a different function. So we'll write this as phi n of zeta. So this un of zeta by alpha will write some function phi n of zeta. All right. So the function of x now becomes a function of zeta, and we denote the changed function as phi of zeta. All right. So we can now change d square u by dx square is equal to m omega by h bar d square u by d zeta square. That's one thing that we'll do. And instead of un of x, we'll now write phi n of zeta. Okay. Now with these changes, the equation becomes d square phi n by d zeta square plus 2en by h bar omega minus zeta square phi n is equal to 0. Okay. Now this is how we did it. We had already brought our equation to the form h bar divided by m omega d square u by dx square plus 2en by h bar omega minus m omega by h bar x square is equal to multiplied by un of x equal to 0. Right? We had brought our time independent Schrodinger equation to this form. Okay, and we made the substitution. We made the substitution that zeta is equal to square root of m omega by h bar multiplied by x. Okay, and we found that d square u by dx square will now become, okay, it became m omega divided by h bar multiplied by d square u of zeta by alpha, because x is now written as zeta divided by alpha, u of zeta by alpha by d zeta square. All right, so d square u by dx square will now become m omega by h bar d square u by d zeta square. All right, now if we substitute this d square u by dx square in here, this h bar by m omega will cancel with this m omega by h bar, and this term d square u by dx square now becomes simply d square u of zeta by alpha by d zeta square. Okay, and the other terms are just like this. You have got 2en by h bar omega, which does not change, and this m omega by h bar x square is simply zeta square. Okay, and here again this un of x will now be written as un of zeta by alpha. All right, so this function un of zeta by alpha can be written as a function of zeta. Right, it will be some other function. It's not the exact same function as un, it's some other function. So let's denote this as phi n of zeta. So let's now write un of zeta by alpha. This is certainly some function. Let's say phi n of zeta. We can write this as a function of zeta. Okay, so this equation becomes d square phi n of zeta by d zeta square plus 2en by h bar omega minus zeta square phi n of zeta is equal to 0. That's exactly what we have here. That's exactly what we have here. All right. So the substitution, the clever substitutions that we carried out changed the Schrodinger equation, the time independent Schrodinger equation, into this form. Okay. Now we see that this looks very much like the differential equation satisfied by the orthonormal Hermite functions. What was the equation again? Right. So if you remember from our revision, we know that the equation that satisfied, the differential equation that is satisfied by the orthonormal Hermite polynomials were, we could write this as d square phi n by d zeta square, Right? We wrote it in terms of x, but it doesn't matter. We'll now write it in terms of zeta. Okay, so d square phi n of zeta by d zeta square plus, here we had 1 plus 2n minus zeta square phi n is equal to 0. Right? We see that our time independent Schrodinger equation for the simple harmonic oscillator has come exactly to that form. The only thing we need to do is to write 2En by h bar omega equal to 1 plus 2n. That will give us the energy eigenvalues. Right, that's simple. But let's first talk about the energy eigenfunctions. Let's talk about the energy eigenfunctions. Okay. Now, the solution to this equation is obviously the orthonormal Hermite functions, right, which are given by phi n of zeta is equal to 1 by square root of pi 2 raised to n factorial whole raised to 1 by 2, which was the normalization factor, exponential minus zeta square by 2, hn of zeta, and hn of zeta were the Hermite polynomial, and together this is the orthonormal Hermite polynomials. These are the solutions to the equation that we just wrote down. Right? So this is in terms of zeta. What we need is un of x. We need to find un of x from here, right? So we have to make the substitution back. We'll take zeta is equal to alpha x, right? And one way to find un of zeta, the normalized energy eigenfunctions, right? Sorry, we need un of x, which are the normalized energy eigenfunctions. We can find it from this one, right? For this, we'll use, okay, one thing we can do is we can use the normalization condition, right? Because we are trying to find the normalized energy eigenfunctions. So let's write let's write the normalization condition. The normalization condition is written as inner product of phi n of zeta with phi n of zeta is equal to integral minus infinity to infinity phi n star of zeta phi n of zeta d zeta equal to 1. This is the normalization condition. All right. Now let's make a substitution. Zeta is equal to alpha x. All right. So this would become phi n star of alpha x, phi n of alpha x. All right. If zeta is equal to alpha x, then d zeta is equal to alpha dx. So we have got alpha dx equal to 1. Now let's distribute this alpha into both these terms, because we can write this alpha as square root of alpha multiplied by square root of alpha. So the normalization condition now becomes minus infinity to infinity, integral minus infinity to infinity. I'll write this as square root of alpha phi n star of alpha x, okay, and then square root of alpha phi n of alpha x dx is equal to 1. Now here we have got the functions of x, right, which are the energy eigenfunctions. Right, we got the result actually. The energy eigenfunctions are square root of alpha phi n star of alpha x and square root of, the energy eigenfunctions are square root of alpha phi n of alpha x. Right, we are looking for the normalized energy eigenfunctions. That's why there's an extra square root of alpha here. Right, so normalized eigenfunctions can now be written as square root of alpha phi n of alpha x. Right. So instead of zeta here, we just put alpha x. It becomes, there's an extra square root of alpha here, right? To make sure that it's normalized. So this becomes square root of alpha phi n of alpha x. So it's square root of alpha divided by this normalization factor, and exponential minus zeta square by 2 is now written as minus half alpha square x square. All right. So we are simply writing zeta is equal to alpha x in here, and this is hn of alpha x. All right. These are the normalized energy eigenfunctions, right? And this function of x we can simply write as un of x, right? So these are un of x. Okay, so what's un of x? It is square root of alpha phi n of alpha x. Un of x equal to square root of alpha phi n of alpha x. Okay, this function of x, which is normalized, we call as the energy eigenfunctions. So we have got un of x, or we have found the energy eigenfunctions. Okay, we got the energy eigenfunctions. What about the energy eigenvalues? The energy eigenvalues are obtained by comparing the two equations. All right, we had two equations. One equation was d square phi n by d zeta square plus 2en by h bar omega minus zeta square phi n of zeta is equal to 0. Okay, this was the equation that we got from the time independent Schrodinger equation. We compared this with the equation satisfied by the orthonormal Hermite function. So we had d square phi n. We compared this with this equation, d square phi n by d zeta square plus 2n plus 1. I think we wrote it as 1 plus 2n minus zeta square. Phi n of zeta is equal to 0. Right? We found the energy eigenfunctions. So the equation exactly works if 2en by h bar omega in here is actually 1 plus 2n. We are just comparing these two equations, which means that, let me write it like this, 2en by h bar omega from here has to be equal to 1 plus 2n. Okay, which means that 2en has to be equal to 1 plus 2n multiplied by h bar omega. Sorry, 2en. Or En is equal to half plus n h bar omega, or simply in a more familiar form, it's n plus half h bar omega. We got the harmonic oscillator energy eigenvalues. Okay, we are done. We have found the energy eigenvalues and the energy eigenfunctions. Okay. All right, let's look at the time evolution now. The time evolution is simple because we know that these are stationary states. The time evolution is very simple. The time evolution of an energy eigenstate is given by simply multiplying it by this factor, e raised to minus I en t by h bar. So this is the advantage of working with energy eigenfunctions because they have a very simple time dependence. Okay, and if you want to write En by h bar omega, sorry, En by h bar as omega n, we get psi n of x comma t is equal to un of x e raised to minus I omega nt. This is how the energy eigenfunctions evolve in time. Now, as we said before, an arbitrary wave function is a linear superposition of all psi n, right? So there's no n here. An arbitrary wave function psi of x comma t is a linear superposition of all psi n. So this is the general solution with the time evolution. We write psi of x comma t is equal to sum over n cn psi n of x comma t. Or we write psi of x comma t is equal to sum over n cn un of x and e raised to minus I omega nt. All right. So we make a note that the wave functions representing state gates are time dependent and the operators are considered time independent. All right, because we are working in the Schrodinger picture. We have thus followed the Schrodinger picture in the above treatment because we have considered operators as time independent and states as time dependent. Right? Only we are working in the coordinate representation, and states are now represented by wave functions. That's all. Right? So we are done. Okay, we have solved the Schrodinger. We have solved the simple harmonic oscillator problem in the Schrodinger picture. Okay, and we worked in the coordinate representation. Okay. Before going into the next section, let me just summarize. All right, we did a lot of mathematics there. Okay, let's just summarize for a quick reference. Right. So the Schrodinger equation for the simple harmonic oscillator is this. This is the Hamiltonian in the coordinate representation. All right. So we have got the energy eigenvalue equation in the coordinate representation. Right. Now we made the substitution. Actually, when we discussed it, we motivated. Right. We gave a motivation as to why we use this particular substitution. Right. But now let's say that we just make the substitution. Zeta is equal to alpha x, where alpha is square root of m omega by h bar. Now, if you make the substitution simply, right, make some rearrangements, you will see that this equation simply reduces to this form: d square phi n by d zeta square 2en plus 2en by h bar omega minus zeta square phi n equal to 0. Now we compare this with the differential equation for orthonormal Hermite functions, right, which we already know. And by comparing, we see that the solutions to this equation are the orthonormal Hermite functions. This is exactly of the form of the differential equation for orthonormal Hermite functions if we identify 1 plus 2n is equal to 2en by h bar omega, which we did, and it gave us the energy eigenvalues, which are n plus half h bar omega. Right? We got the energy eigenvalues. And the energy eigenfunctions are simply the orthonormal Hermite functions. Right? And we saw that this energy eigenfunctions of un of x, the normalized energy eigenfunctions, are square root of alpha phi n of alpha x, right? Where phi n of alpha x is given in this standard form, which we already know, right? We already know the function called orthonormal Hermite functions, okay? And the energy eigenvalues is repeated here. It's n plus half h bar omega. And in the end, we talked about the time evolution, right? So wave functions representing state gates evolve with time because we are working in the Schrodinger picture, and operators are frozen in time. Okay, and the wave functions evolve according to this equation. Actually, the energy eigenfunctions evolve according to this equation, and the general wave function can be written as a linear superposition of all the energy eigenfunctions. Okay.